difference does it make? Yes.
Is it to prevent the axon from touching the muscle cells?
I don't know if that's involved, but I do know it makes it go faster. It speeds up your action potentials and your signal.
So that it doesn't get lost in the rest of the body?
It's gonna go along here, but it's gonna go along here faster.
Keeps it from leaking out, right?
No, I'm just saying, like, if it's an electrical signal, the actual electrical signal, then it would get dissolved in water eventually.
It could, but this is really small, so we're not worried too much about that. The distance is real close here.
No,
But
I'm just thinking of the reason why you would insulate that part specifically.
well, you don't up here, that would be a mess, I think.
Yeah.
So here, you do it, and it speeds up the message, the neural impulse. Neural impulse goes faster. Neurons that don't have myelin on their axons, the unmyelinated ones, go slower. Yes.
If they're myelinated, how can you have an axonal synapse? Because wouldn't the myelin prevent the transfer?
Well, these things can stick their boutons in there, kind of inserted. So that I don't think is a real problem. And these are small distances, and all they have to do is send the neurotransmitter through and get some in, so you can have your communication. But they don't touch. They're not supposed to be touching in most cases. Okay?
So it's not touching your mind?
It's not, well, no. Well, it's not touching the other neurons. The two neurons are not touching.
The buton on the one is not actually physically touching.
Right, right. That would change things if they were physically touching. Because here, if they're not touching, you can do things with that. You couldn't do them if they were touching. You can control it, okay? So, let's look at this. This is now page 393. All right, I used to say, Queen Elizabeth, how many times do you think she got down and scrubbed the floor?
Twice.
How many?
Twice.
Twice? I'd be surprised if she even did that, okay? She had people to do it for her. She had all kinds of servants, okay? People that were hired to do these things for her. I bet she didn't do much in the way of washing dishes either, right? I mean, if she had a glass or something, she might have rinsed it out, but do you really think she'd sit there scraping off the lasagna? I just don't think so, okay? So, why I'm saying that is the neurons in the brain and the spinal cord, they think they're royalty too. So they have helpers. How many helpers? Each one has about average 10 helpers, and the helpers have a name. So let's look at the note sheet. Here's all that neuron, cell body, axon, hillock, it's all there. Myelin. We got one more thing we hadn't said here. But the helpers are called neuroglia. Neuroglia. 10-to-1 ratio. Now we have to look at these terms because I didn't want to skip over them, because this is something we were talking about earlier that you need to know. What's a nerve? It's a bundle of axons. What's a tract? A bundle of axons. What's the difference? Where they are. If the bundle of axons is in the PNS, it's a nerve. If it's in the CNS, it's a tract. You've already run into that. Name the tract you learned. I want the name. Before which tract? Starts with hypothalamic, hypophyseal tract. And where'd it go?
To the anterior.
It's from the hypothalamus to the,
Anterior pituitary.
no,
Posterior.
posterior pituitary. So what's it gonna send down into the posterior pituitary?
signal to release hormones?
That's gonna be happening, but it's gonna send physically what down there, the hormones, to be stored, and who are they? What hormones are stored in posterior pituitary? ADH, antidiuretic hormone, and who else? Oxytocin for the pregnant female to go ahead and have labor, okay? So those are the two hormones that are not made in the posterior pituitary, because it doesn't make any, but are sent to it from hypothalamus. How many hormones did the anterior pituitary make? 6 of them at least. Where's this hypophysis stuff?
The name of the pituitary.
Name of pituitary, technical name for the pituitary, hypophysis. Okay, so we know now nerve and tract. Tract is a bundle of axons in the brain and spinal cord. Nerve is a bundle of axons in the PNS. The biggest one we talked about was sciatic nerve. Now let's talk about a ganglion. Ganglia, that's plural, ganglia. Ganglia are not in brain and spinal cord. They're in the PNS. They may be close to the spinal cord, but they're not in it. A nucleus, plural nuclei, is a group of neuron cell bodies in the brain or spinal cord, CNS. A ganglion is a group of neuron cell bodies, but in the PNS. So you gotta keep track of these so you get it right. Right? Yes.
Why is it specifically saying neuron cell bodies instead of just like neurons?
Because it's the neuron cell body, it's not the axon.
Just the soma.
It's just the soma part. Yeah, and it's got the nucleus in it too. So there are things called dorsal root ganglia. Where would you expect to see these? They are close to the spinal cord, but tell me a little more about their position. Dorsal root ganglia. What's dorsal? Give me the opposite.
Ventral.
Ventral. So dorsal is more to the back, ventral is a little more to the front of the spinal cord. So you gotta watch all these little inflections here and little things so you know what you're talking about. Neuroglia are the helpers for the neurons, ratio 10:1. So there are 4 of them that are in the brain and spinal cord, CNS. There are 2 in the PNS. So you gotta keep thinking about it because some are in one place, some are in the other. The most common CNS neuroglia are astrocytes, and they touch neurons and capillaries. And it's a little bit unclear what they do, but they are connected to holding on those places and regulating the nutrition from the blood vessels and even neuron transmitters. So then the question is, most common CNS neuroglia are astrocytes. The microglia, what do? They're special like macrophages. And you say, why do we need special ones? Because there's a blood-brain barrier. So things in the blood don't just jump over into the brain or don't just jump over into the spinal cord. There's a barrier, blood-brain barrier. So that means your immune cells, like macrophages, are told you're not allowed to come in here. So macrophages can't just go to the brain, even if you're under attack. So we say, what do we need to have if we can't use the macrophages, the immune cells? Then you need homegrown microglia. So in the brain and spinal cord, you got microglia. They are considered neuroglia. And they can convert into special macrophages. And what would they do? Fight disease or invaders. They could also eat debris, because they act like macrophages. They would eat dead things, dead cells and stuff. But you have to have microglia in there because the macrophages can't go in. Blood-brain barrier. Prevents your white blood cells from coming in. Okay? Now, you got fluid in your brain and your spinal cord and it moves. How does this fluid move? Well, it's not being pumped by the heart. So how does it move? How does it move? Cilia. Old cilia moving around. Where are the cilia? They're stuck on the outside of ependymal cells. So ependymal cells have cilia that moves the fluid through the brain and spinal cord, and that fluid is called cerebrospinal fluid. Don't make the mistake, learn it correctly, it's cerebrospinal fluid. Okay, it's not cerebral. That's what a lot of students do, they mark it cerebral and I take up points. Okay?
Does cerebral spinal fluid surround the brain?
Uh-huh, and it flows through parts too. And it flows down the spinal cord, and it flows back up again, so it moves around. But a heart doesn't pump it, that's not how that works. It's by these cilia on the ependymal cells, okay? And now, get to the insulation on the axons. If you're in the CNS, the insulation is actual living cells called oligodendrocytes. Oligodendrocytes. You all do know there's something in the dictionary that you can go to and it will pronounce words for you. Everybody knows that. You might, if you don't, you could investigate it. So if you don't know how to say this, type it in and see what it says. Okay. And so the myelin in the CNS, brain and spinal cord, is actually oligodendrocytes, living cells. So it wasn't living what your cat chewed up on the light cord. But these are living cells, oligodendrocytes, but only in CNS. If you get into the PNS, you get little jelly rolls called Schwann cells. Schwann cells, they sort of look like jelly rolls. That's where I came up with it. The book doesn't call it that. So I'm going to take you to picture, page 395, and there you go. I showed you the other one. This is from the book. And this is the neuron cell body with the nucleus. What are these little vitamin capsules? Mitochondria. And this neuron cell body has the twigs coming out here called dendrites. And it has the axon hillock leading into the axon, who goes down to the ends with the boutons. And see all the jelly rolls? Only on axons you put the insulation. Not all of them have it, but some do. These are insulation, living cells on the axon, PNS. How do you know that? Because these are Schwann cells, and Schwann cells are only PNS. They're not CNS. Oligodendrocytes will do similar stuff in the CNS. So we got Schwann cells, and this speeds up the neural impulse. And the odd thing is, the insulation has openings in it. And the openings are called,
Sheath gap. It's on the other side.
I thought it was right here, but I didn't see it.
It's right there. And a little bit more to the left.
Just under the picture.
Oh, myelin sheath gap.
Yeah, then I've got another name for it. Nodes of Ranvier. Nodes of Ranvier.
What would be the objective of leaving a gap in between the sheaths?
That's the first question you ask. Why leaving gaps? If it was your electric cord for your light, you'd say this is horrible, okay? But it's actually helpful. The signal goes faster. Let me ask you a question. What do you think? Can you go faster just walking or skipping? Skipping, although you might be a little clumsy at it if you haven't been doing it. But the signal skips from node to node to node, nodes of Ranvier. The signal skips, that makes it go faster. Interesting, isn't it? So it's not a problem, it's a help for having nodes of Ranvier so that the signal skips from node to node to node instead of going along in a continuous fashion. They would call it a continuous manner to do it if you weren't going node to node.
So the Schwann cells act like an impulse generator, not in the sense that we're talking about, no, more like a, I'm lacking the words.
Okay, they're working to insulate this, but they speed up the neural impulse by letting it jump from node to node to node. It doesn't have to go through this, it skips over it.
So do both CNS and PNS have like that setup?
No, because PNS is the only one with Schwann cells. The other one, the oligodendrocytes, they have nodes. I'll take that back. They have nodes, but they're not the jelly roll. So when